First of all, I want to thank the organizers, Hyungju and Leonard, for inviting me to this conference. And it was also nice to see the people, some people whom I haven't seen for quite a while. So today, also before I start, so actually the poll was very nice to allow me to throw this chalk or eraser, right, to people who get sleepy, right, during my talk. So hopefully it won't happen. So anyway, so today,
what do you do to somebody snoring?
Oh really? Okay, so keep me informed. Okay, so title is a little different from the one in the abstract notes, because at the time I wasn't sure what to talk about, and very recently I decided to talk about this regularity theory in the Vlasov Poisson system, which concerns these boundary value problems. So I'm working with the boundaries, so we'll see what's going to happen there. So the content of my talk would be the Vlasov Poisson system. I think that many of you already know what this system is about. And then, so for those who are not that familiar with this system, so let me give you some warming up, simple, basic estimates, and then this is the point of my talk. So since I'm working in these domains with boundaries, so I will introduce some boundary conditions for my equations. And then I will state the boundary value problems in terms of regularity. It means, in other words, I'm interested in this global existence, but the classical solutions. And that's why I say the regularity here. And well, I was working on this half space and bounded domain. So we'll see. Okay, so maybe that's nice pictures. Well, so you see these two pictures, and there are the electrons and stars, but we can think of them as particles, and they move somehow. So their movement are driven by some self-generating forces. Which one is electric field, and the other is by the gravitational force. So their behaviors are almost same, except for the directions of these forces, the fields. So one is repulsive in this case, but the other is, of course, attractive. So we'll see how this the particle descriptions are like. Okay, so well, there are several levels which you can describe this the movement of these particles. Or you could approach a very microscopic way, or very fluid-like description you could approach. Yeah? But this Vlasov Poisson is just in between these two descriptions, between microscopic and macroscopic. So that's why this Vlasov Poisson, or Boltzmann, including Boltzmann, is called mesoscopic description of interacting particle systems. So well, this is one way to introduce this system. So we look at the particles in say with this distribution sense. Okay, distribution, that's the function. So we call f. So this f depends on three variables: position x, velocity v, and time t. And then, of course, this is very, very known. And well, basically, Vlasov equation is due to this Liouville equation. Okay, So this is exactly the Lubin equation. So the rate of change of f along this characteristics is due to these collisions. This is very well known. Instead of looking at this Vlasov theories, looking at these characteristics. So this is just the f equals ma. So when Newton's second law, nothing else. Okay. So since I'm concerning these boundaries, so with especially the bounded domains, so I will more concerned with this plasma case. So and also I neglect this collisional effect. So therefore, so we have a Vlasov equation coupled with Poisson equation here. So this plus means we are in this plasma case. Of course, we start with initial condition, but the boundary conditions will be, it will be manifolds. Therefore, I will skip here. So I'll postpone a little bit. Okay, so before we start, so we get into the real business. So let me start with this very basic estimates. First, one of the basic properties in this Vlasov Poisson system is, of course, so this is the way how this f was defined, the Vlasov equation was defined. So the f is constant along these characteristic equations. This is, you can see easily. And second thing is, so I said Paul the other day, that this Vlasov Poisson system is indeed one of the Hamiltonian systems. So therefore, we have this nice property of measure preserving thing. So therefore, we have this. And now, more than that, we also have the energy conservation thing along this Vlasov Poisson system. So you just do the standard, the energy estimate, and follow all these things, which I will skip, just in showing you this could be exercise for grad students. So finally you get this the energy conservation here. So this is easy exercise for students. Okay, now so let me address the problem of my talk. So I am interested in this global existence of classical solutions. Okay, so in kinetic community or kinetic theory, this is well known. So what's the key point of going from, say, passing from local to global existence? Of course, the local in time solution was known for a long time ago, but the concern now is whether or not we get global existence. So this is a big gap. But well, the key quantity to prove this is this one. So this is the velocity in support, okay, in the support of f until time t. So whether or not the velocity, right, is bounded globally in time. This is the key point. So this is where I'm not gonna go to this point. But suppose we understand this, then the thing is now whether or not we can get global bound of this quantity. Okay, so this is the theorem. So Q is bounded in any time until any time, then we're done. So the game is done. Okay, so well, we have this a-priori estimate, which is simple. So LP conservation and energy conservation, or the boundedness. This is kinetic energy. Anyway, so with this, so before I get to the problem, I want to point out why this is non-trivial. Why this problem is non-trivial. So because as I said on the previous slide, say the thing is whether or not we get the global bound for this the control of this q of t, the velocity. Well, the jump of the velocity is bound, actually controlled by this one, acceleration. So this is electric field or acceleration. So now, so you go to the potential theory with the green function, and this guy is bounded by this, of course. Okay, in R3, we are in R3, and then you do this, interpolation like that. So when x minus the bottom is small and big, so we split into two parts like that, and then for the first part, you bound by this. Basically, you use this one, okay, at infinity, and this one is the L5/3 norm, which is the optimal norm, I would say, before doing anything else. Okay, so natural one. So we use this norm, which is bounded, okay, in time, global in time. And then you do display with the parameter r. Then blah blah blah. Of course, this rho is the macroscopic density, okay. And then of course that is bounded by q over the power of 3, right? Because we are in R3. So you compute the power there, then you exactly have over 3 here. So that's the point. Then you just do this, right? Then you have this guy. Therefore, you just simply applying the Gronau, the usual Gronau inequality, won't get you this the global bound in this Q, the quantity Q. So that's the right. This is why we have to do something more. Okay, so far we have, this is of course without boundaries, okay, for the whole space case. So there are two methods available for this global existence problem. And the first one is first introduced by Lyons and Pfaffelmoser in 91, and this is called high velocity moment technique. In other words, this is that method. So in that paper they proved this is bounded, okay, for sufficiently large M. If this is done, then we can easily prove that this is bounded. Then we are done, of course. So this is one way. Of course, this is very nice method, elegant method. And second one is, this is very different method. Okay, so the first person who tried this one is Pfaffelmoser's idea in the whole space case, and his idea basically they use, say, this the small time interval delta, and then play with this the delta, but he looks at this integral, triple integral, and then so he do the estimation in different say part at the spaces. So one is good and bad and ugly. Okay, this is good, and so actually in his paper he didn't say about this good. He didn't name these sets, but you know who did this? He's the Jack Sheffer in CMU, and the story about the behind story about this story behind this one is the following. Actually, his paper is really hard to read or understand. So that's why Jack Sheffer tried, and also other people tried to say simplify and make it more say understandable. So that's why the subsequent the papers were published. And in Jack Sheffer's paper, he actually named this good and bad and ugly. And now you can see why these names are made this way. Of course, good set is good, bad is bad, but it's okay to control. But the ugly is the most the very nasty actually. The set we'll see. And anyhow, so I'll show you how this the very delicate estimate can be done. Okay. So, okay, so we have to, for instance, we have to show this. Then we are done, okay? I'm not going to go to that. And now, so the real boundary issues here. So, of course, we have two quantities for my equations. So one is F, okay, the density distribution F. And for F, so of course there are other, say, boundary conditions, but for my talk, I will consider two, okay, two boundary conditions. One is for, inflow condition, right, or absorbing condition. So F is the prescribed by Z at the boundary, and not exactly at the boundary, but for incoming, okay, incoming velocities. And the other is specular reflection, and which means, you know, that this is the, you know, reflected velocity, and F has this, you know, equality. This is specular reflection boundary condition. And now there is another quantity in my equations, that is the electric potential V. And here, so we consider two boundary conditions, which one is Dirichlet and the other is Neumann. Okay, so this is the Dirichlet, and Neumann is, of course, so as you can see in this picture, this is Neumann. Okay, so we consider these two. Okay, now you can see the combination. So how many combinations? So at least 4. So we'll see. Okay, this is initial boundary value problems. Now, so we start with this, and of course, later on, so I'm gonna specify boundary conditions, case by case. And well, there are. Okay, so what's the key points in my problem? Is I would say two issues. So one is actually the control of Q of t, which was in the whole space case. So this one was actually existed in the whole space problem. So this is, of course, the same problem in the boundary value problem, but this one is actually new one. Okay, this was new one in boundary problems. So because basically the problem is this. So the boundary. So we have, say, boundaries, right? And this boundary is exactly characteristic for the Vlasov equation. So that is the problem. Therefore, it means the singularities, right, are generated from these boundaries. And then the thing is, the problem is whether or not. So we want to prevent these singularities, from propagating inside of the domain. That's the game. Okay, so how we can avoid that propagation of singularities inside of the domain. So that is another issue. So we have to consider these two, okay, obstacles. And now a little bit of history. So of course the whole space case global existence has been done by many people, starting from Bard, Horst, Bardos, Digong, and etc. etc. And for, say, stationary Vlasov Poisson system, Papu and Gringer and Lavia is some nice results, had obtained some nice results. And also the initial boundary value problem has been attacked in the weak sense, so by these people. Okay, and now, as I said, the problem is the classical solution. Okay, so the first, as far as I know, the first person who tried this problem is Jan Guo. And well, for instance, in this paper in '95, and where he did this, he considered this absorbing specular reflection condition for F and Neumann for electric potential. For instance, this is half space without any curvature, and okay. And then so this is the story. So actually, he's my former advisor at Hwang, and actually, at some point I asked him, so why you didn't try traditionally boundary condition? So very carefully, okay, so not to hurt him, and very carefully I asked him, why? What's the reason you didn't do this with this, usually boundary? He just, he said just that. Well, it's because I wanted to know it's a trivial, right, game or not. I just wanted to know, and he said, well, it's non-trivial, but he just didn't do. Okay, so it's a good sign anyway. So I wanted to think about the problem. So he just said it's non-trivial at all. So we tried, and this would, and recently we had some result for this threshold problem. So I can show you. So what's the big difference, right, from the Neumann problem? And then our real business was actually in bounded domain, and this was actually the one part of my thesis problems. And so this, in bounded convex domain, as you can see, so going from this flat case to the curved case is a lot more difficult to me. So and then at that time I tried hard, but I couldn't do, I couldn't complete the problem in the sense that I only did the observing condition for F, and of course for electric potential I could do usually Neumann, but I couldn't do a specular inflection case. In that sense, that was in a sort of incomplete work. And of course, in this instance, I only did this specular reflection with spherically symmetric assumption, restriction. So at that time I was happy with that, but I wasn't extremely happy. So that was the small gap. And then after my PhD, and I went to other problems, but time to time I came back and think, so what's the solution? Anyway, so that was a little story about this problem. And then finally, so I met this guy in Max Planck Institute, and then we talked a little bit about this thing. And then, recently, so we finally solved this problem, specular reflection, and it was not so easy to complete. Anyway, so I'll get back to that. And then, so the only remaining, problem is, of course, Dirichlet. So Hyungju again. So I see him time to time, of course, in conferences and so on. And he said, why don't you finish everything, of your problem? So he suggested, and then I might. And then I came back, and then so I suggested my student, one of my students, to work on this, and then it's in progress. Anyway, so this is whole story about one of my problems, and so let's get back. Let's get back to the issues, problems. So this was, as I said, half space case, so without curvature, but Dirichlet boundary condition for phi. So this was the only difference. And of course, so this theorem basically says we obtain classical solutions in Holder space, in Holder norm. Okay, so this now, so let me briefly talk about this. Talk about what is the difference, So, Neumann boundary condition, as I said, there were two issues for this problem. So one is how to deal with these singularities, generate from the boundary. And this one is actually we have to first, we start with this functional or reactional functional defining singularities. And then we want to control this guy in time. So that was the point. And well, in Neumann boundary condition case, we defined alpha as follows. Well, as you can see here, suppose this is hyperspace, and so hyperspace defined by this x1 equal to 0. Okay, so therefore you can easily see this is actually defines the singular set, and you play with this guy, okay, in time, and that way you can, you know, maybe I'll explain a little bit later on. Anyway, but usually boundary condition. What's the difference here? So instead of using this guy, we use this. So well, you can say this is, oh, this looks simple, right? But this is somehow you have to jump, right, from this idea to that idea. But anyway, so this perfectly defines the singular set, and what's the, you know, what is the better in this case, in this functional? Well, you see, well, as I said, you have to control, you have to look at the time evolution of these quantities. Then you have to take a t derivatives, right? Then you have to deal with this, you know, time derivative of electric field.
What is the one referred to?
One, as I said, so say the first coordinate. Let's say hyperspace, right? x1 through xn, okay? And this is, so hyperspace can be defined this way. So that's how, so well, as I said, this is 0, define the singular set at the boundary. And, but as I say, you can see this, well, t derivative of the electric field and t derivative of potential. So which one is easier? Okay, I can ask Paul, so which one is easier? So of course the P, you know, P is easier to deal with. Because electric field means the gradient of, sort of, you know, gradient of P. So therefore it involves more derivatives, much harder to deal with. So that's how somehow, so that's how we could, right, control this guy. So we'll see a little.
Is this still the plasma case?
Yeah, we are in the plasma case, of course. Yes. Okay. So this is the oh, sorry. But this is so-called the velocity lemma, so which tells you this thing. So we want to prevent singularities from propagating into the domain. So as I said, you control this guy, okay, the functional in time, as you know, time goes to infinity. And well, so this lemma says basically this quantity can be controlled in time. Okay? This means, of course, for any finite time t. Okay, so this is the lemma of this this singularities. So maybe a little bit of proof. So the beta, as I said, we define in this way, it's different from the Neumann case. And then you take the, you know, time derivative as usual, and then, well, you know, using the characteristic equations, you have this you know, identity. And now, as I said, instead of, you know, dealing with the second derivative of phi, now, so we can just, you know, deal with the first derivatives, yeah, space, tangential derivatives, and the time derivatives. So this was much better than the, you know, the two derivatives, second derivatives. And then a little bit proof, maybe. Okay, so just a little bit. So well, basically this is the key thing. Actually, the key thing is, so this, you know, the method, this one, indeed, time derivatives and tangential derivatives of the, you know, phi can be bounded by this guy. Okay, so at least the log. So this is a key thing, actually, key estimate. And then suppose we have that, then basically you finally get this thing, okay? So therefore, this, using the superbronner inequality, so you win. Okay, so this is the proof.
Can you say what motivates to use this beta, the form of beta? What motivated?
Well, of course, motivation is in the normal case, right? You can define this is kind of like a reactant functional. So singular set. Okay, so the thing is, so suppose this is our domain, and then the reactant functional we want to construct. So suppose here, so start from whatever the reactant functional. So in normal case we call it alpha, right? So it's 0, and then so you somehow evolve, okay, the constant values, okay, and then and so this alpha is not has either positive or negative. I think that I don't remember. But anyway, somehow this thing we want to somehow play with. Okay? So, but Neumann case, we just did this way, minus E1 X1, things like that. Okay? So this perfectly defines this, and you can say separate, right? The singular set and non-singular regular set. And now, as I said, if you just use this same reactant functional, right, in the Dirichlet case, then you have to deal with this, for instance, time derivative. Okay, you have to look at the time derivative of alpha, and this is two, as I said, second derivatives of potential, which is hard to control. So, and then the Dirichlet case, we wanted to come up with new functional, which, but nevertheless has the same role of this function, okay, separating singular set and non-singular set, and that is exactly this beta. Okay? So minus p and x. What's it? And we have so this one, the blue. So this looks like kinetic, right? So of course in this singular coordinate, right? Kinetic energy and potential energy, things like that. So this is the case. This perfectly defined this kind of energy in say singular direction. So that's the idea. Then, well, okay. So in that way, you can finally gain the game. So whole estimate, and then that's the one story about half space, and so now the second story is about the real hectic problem, that convex bounded domain. In half space case, for instance, what's the difference? One difference would be the following. First, so you follow the trajectories, right? First. Well, for space case, suppose for simplicity, let's assume there is no field, okay, no acceleration at all. That the characteristics would be just straight lines. Well, for space case, just straight line, and you can go to a period, forever, no problem. But now, so you have bounded. So if you assume the specular reflection, then you just hit the boundary and then reflect. That's it. So only one. But now you say it is bounded convex. Well, even without the field, it's really hectic, and with acceleration it's even worse. Okay, so that's why this problem obviously, to me at least, difficult problem. And then so we can get almost saying the conclusion here in this case. But the Neumann case, and well, maybe a little bit I can tell you. So first of all, now, so for this problem, I'll address a little bit of issue of this QOT, one of the 2 points for global resistance. And now, so you can play with this small time interval in this estimate, right? In this estimate, and you choose, well, this is parameter which will appear in later. And what's this? What's this? So this is what basically q to the forward 3. This quantity is basically the effect of electric field. So you have seen before in the crude estimate, and that was exactly the effect of electric field. And now, so you say so, and then the goal is to estimate this guy. As I said, well, if you want to follow with adapt the method, the idea of Pfaffelmoser, you split into 3 space, the good, bad, and ugly. And then, well, so this is parameter P, and then the other one here. But the difference here is, well, as I said, well, okay, so maybe. So we have, for instance, like that. Okay. So you actually consider the difference of the 2 characteristics. Okay. Now, well, you have 2 parts, actually 3 parts, but basically 2 parts, because this part and this part can be thought of in one case, as one case, because you can just reflect here. Then that will be just one. Let me go like that, right? No. So what is that? I want to reflect this one. This? Am I right? Yeah? No, this one. So let me see. And this one, okay? Yeah, this is right, okay? Well, it should be this is like that. And this, okay? You see what I mean? I reflect, okay? And then the middle one is just missing. Okay, you can consider it as one, but the problem is here, okay? In the middle one, you can think that one as in one case. So therefore, you have to think of this reflective, okay, point. So you have to modify a bit. So, well, all these things, and then the crucial thing is somehow this separation property, and now indeed this separation of x, right? Separation is at least linearly, okay? Can be separate from each other at least linearly. So this is what this says, and but you have to somehow, well, consider this guy. Okay. Of course, what I'm saying is it's non-trivial in the sense that, well, this is geometry, and you see even in the half space you have a lot of, right, the intersections like that, right, and then of course you can split on each at each intersection point, but how can you compare with each other? That's a big story. But you can just this one you can just consider them, classify them as into only 2 cases. One is this unreflected, right? Unreflected case, and the other is reflected case. Somehow that's a non-trivial to prove, but this is what this theorem says. Anyway, so this is one of the crucial things. And then, so this is the story about the proof. So, well, in the good set, you do the velocity integral first. Okay. So in that way, you have this thing, and P is the this one. P is a parameter, okay, in the set, defining set, and then in the back step, you do space integral first. In that way, so you have this, okay, this quantity, and finally, as I said, the ugly set is most difficult 1. And so here exactly this separation property was applied. Okay? And finally, so here of course time integral first. You do that. And then finally you have this one. Okay? And putting this all into 1, so you have this thing. Okay? Now how can you choose this guy? Of course, if you can choose, you can choose this parameter in terms of Q in this way, then you end up with finally this thing. The beta here is less than 1. You can choose. So we won the game in this way. So this is the proof goes. And now, so let me say a little bit about the curvature case, okay, curved case. And now, well, as I said, well, this was the starting point. In the half space case, here was the Q to the 4/3, which is the effect of electric field. Now, as I said, not only this electric field, we have curvature. Therefore, we have some other force driven by this curvature, which is indeed turned out to be this Q. Yeah, exactly, Q to the 2. So somehow this curvature effect is stronger than electric field. So this is the thing. Okay, this is actually intuitive. The reason why this should be so. Okay, so this is probably so. And so maybe let me briefly mention. So for instance, the total length of that characteristic moves, including reflections, is bounded by Q to the Q times delta. Okay, and we have to also consider the change of the normal vector, because normal vector changes now, and that in a distance of order Li is bounded by this C times Li, and also therefore all this right change of angle of the vectors, two vectors, and then this is bounded by this guy. So this guy is due to curvature, and this is due to electric field. And finally, all together you end up with this guy and this guy. So finally this guy, the competition between two, but finally this curvature term wins. Okay, in this effect. So this is the thing, intuitive way to understand this effect. And if you really want to look at this rigorously, then you do the analysis like this. So you do transform in geometric terms like that. So you say parameterize this, the surface, okay, and boundary like V1 and V2, and then you use normal vector like that. Then you transform in this way. So now you have new coordinates, mu1, mu2. This is normal component, and W1, W2, and this is normal coordinate of the velocity. Okay, in this way. Of course, this is valid near boundaries. And then finally, well, this is actually this computation done in Max Planck Institute. I remember it was a long computation, and then the nicely there. So they're actually having good say blackboard is essential for mathematicians. As far as that's my opinion anyway. So and then so we had the nice advantage of having good blackboard there, and then so we computed all these things. So finally we got this computations. Okay. So here, so all the geometric terms and also plus the electric fields were taken into account here. So I'll tell you this. Well, this one, for instance, is these are of course the velocities, but here you can see this gamma IJL is actually the Christoffel symbols of the surface, and this Vj are the second fundamental form, okay, the coefficients of second fundamental form, and Kj's are principal curvatures on the surface. And that's this way. So now let's look at the characteristic equations. And now, as you get, of course, with these geometric terms, now we look at this. Look at these things. Okay, along the characteristics, what in the evolution, this is a curvature, the effect of curvature, which is q squared. Okay, which is obvious in this equation now. Okay, so this is a rigorous way to identify what we have thought, intuitively. And also, this is sort of the end of my talk. And thank you for your attention.